Hello, this is a calculus video. Could have been a physics video, but we're coming at radioactive decay from a calculus angle. I've been following James Stewart's 6th edition calculus, and this particular section, 7.5, is on exponential growth and decay. In this case, decay. What is radioactive decay? Is that like tooth decay? No, it's not like tooth decay. Radioactive decay is there's certain forms of elements. Not every form of every element, but there are certain forms of certain elements that are unstable, and over time they decay or transmutate into other kinds of elements. You can't do this with gold, unfortunately. I mean, I wish I could, if I take this, it becomes gold over time. No, sorry. But it does happen with, for example, what's called carbon-14. The number 14 is how many particles there are in the nucleus. Carbon-12 with 12 particles in the nucleus is very stable, but carbon-14 is not. It's radioactive. It has 2 additional neutrons, and those 2 extra neutrons make carbon-14 unstable. And over time, carbon-14 becomes nitrogen-14. One of the neutron turns into a proton. You can actually use this for dating. You may have heard of carbon-14 dating. You can actually date something by the amount of carbon-14 that's left in it. Because over time, this is very predictable. There's something called a half-life. In a certain amount of time, half of carbon-14 will become nitrogen-14. There's also potassium-argon dating, because radioactive potassium becomes argon. Radium becomes radon. Uranium becomes lead. Plutonium, and so forth. These are used in atomic bombs. Uranium-235 is unstable. Uranium-238 is not, a difference of 3 neutrons. So radioactive decay. Radioactive decay is one of those situations where the rate of decay, so the change in mass over time, which is negative because we're talking decay, is proportional to the amount of stuff you have. And so all we need is a constant, K, to figure out exactly what this equation is. We call this a differential equation because we have both mass and the derivative, a derivative of mass in the same equation. But basically, the rate of decay is proportional to the amount of material. And so it falls into the category of exponential growth and decay that we've been talking about. I did a video on population growth following the same principle. And again, dm dt is going to be negative because we're losing mass of the radioactive material. We're not losing mass total, but we're losing mass of that particular material. So K in this situation becomes the relative decay rate. In population, K was the relative growth rate, but we're talking decay here. So if I divide both sides by m, the relative decay rate is going to be negative 1 over m dm dt, okay? The relative decay rate. Now, we know if we take the formula from that video on exponential growth and decay, we had the formula y of t, y over time, is going to equal initial y times e to the kt. See the previous video. So if we apply that to mass, then mass in relation to time, because this is one of those exponential decay situations, the mass in relation to time is going to be the initial mass times e to the kt. Now, what k is going to be different depending on the amount of mass you start off with. But if we know what the initial mass we start off with, and if we know the half-life, then we can determine what k is in a particular situation and come up with the formula for what's going to happen over time. So here's the example, the example that's given in Stewart's textbook here. So I've already told you what a half-life is. Let's tell you officially. The half-life of a radioactive element is the time it takes for half of that sample to decay into whatever it decays into. So here's the example. Radium-226, man, that's big, nucleus. It has 226 particles in the nucleus, a combination of protons and neutrons. It is unstable. It's radioactive. It has a half-life of 1,590 years. That means in that many years, radium-226 will decay into radon-222, losing four protons in the process. Actually, I'm not sure how many protons it loses, but it'll lose four particles in the process. But it'd take 1590 years for that to happen. So what would the mass of, what would be a formula for the mass of 100 milligrams of radium after T years? Well, by the way, what is the half-life? The half-life is 1590 years. So in 1590 years, we'll only have 50 milligrams of radium-226 left. The other half will have become radon-222, an inert gas. So let's come up with an equation so that we know how much of this we would have left in relation to time. Okay, so here's the formula again. Mass in relation to time is initial mass times E to the KT. That'll be true for any radioactive decay. So in this particular case, we know that we're starting with an initial mass of 100. So this equation is true, right? We also know from, again, that exponential video that y in relation to t is going to equal the initial y. Let's see. Hold on a second. Let me get my head straight. Okay, sorry. So we know that in 1,590 years, we're going to have half of the initial substance, right? So we're going to have 50 milligrams in 1,590 years. So what we can do is we know that this 100 e to the kt, and what's t? T is 1590. So I went ahead and put it in that order, 100 e to the kt. We know that what's the mass going to be? It's going to be 50 in that many years. All right. So now we have this. We can solve for K and come up with a general equation for this particular situation where you start with 100 milligrams of radium. So we know if we divide both sides by 100, then we know that E to the 1590K, I just switched the order, E to the 1590K is going to equal 50 divided by 100, which is 1/2. So if I take the natural logarithm of both sides, the E goes away like a knot, whoop, where'd it go? And we're left with the 1590K equals the natural logarithm of 1/2. Well, the natural logarithm of 1/2 is negative because it's in the denominator. And then we can bring it up to the numerator if we bring negative out, negative logarithm of 2. Okay, so if I divide both sides by 1590, then I found out what the constant is. The constant is negative natural log of 2 over 1590. Now that I know what K is, I can actually create a formula for the decay of this 100 milligrams of radium. So the mass in relation to time is going to be the initial mass, which was 100, remember, e to the kt. Well, there's the t, and here's the k. Negative natural logarithm of 2 divided by 1590. And so now the example goes on to ask a couple other things, when will it reach 30 milligrams and so forth. But this equation, once we have this equation in hand, we can answer those other questions. And how did we get to this? Is an equation for the specific situation when we begin with 100 milligrams of radium, and this will tell us what the mass will be at any time thereafter. All right, radioactive decay. Another example of exponential growth and decay.